Okay, so hello, welcome everyone. Welcome to the week 8 of RecSys Learning Book Club. Today we'll talk about low rank methods. It's a continuation of chapter 10 from last meeting. So, little introduction about me. I'm Rohan Singh Rajput. I'm a senior machine learning engineer at Headspace. I also lead personalization domain there. If you have any more questions about this book club or any other questions regarding recommendation system, you can connect me on LinkedIn. So this is the agenda of today's session. So first minute I'll do the introduction and about myself and book details. In the next 45 minutes we'll discuss the learning from the book. It depends on how much chapter we cover in that particular book. Uh, uh, and in the next 18 minutes we'll do some discussion on learning if time permits, and the last 1 minute we'll do the wrap up and talk about the next chapter. The chapters will be recorded but discussions are not, so feel free to join the discussion as we are not recording these discussions. So information about this book named Building Recommendation System in Python and JAX. The book written by Bryan and Hector from Google. And the we chose this book because this is one of this advanced state of the art book on recommendation system. It's a highly practical oriented, and it's focused primarily on like building production level system. It's written by industrial professional who had like hands-on experience on building real-time recommendation system. So today we'll talk about chapter 10. So if you recall from chapter 9, we discussed mostly about feature-based method where we try to utilize user and item feature. So we had like two important uh, segments. Like first is the user segment where we try to utilize the user features. This is you, right? Okay. And another one we have so these are like sometime raw feature or like encoded feature where we do some kind of feature processing. And in the V vector, we use uh, item features. So let's say like V or I, whatever works for us. And these are like raw item features. So what earlier we used to do, we used to take all the user features and all the item features, and we use several techniques to generate recommendation system recommendations. One of the popular technique was we try to uh, generate some kind of feature encoding, and that feature encoding will help us to find out similar feature. We saw that we can use both like collaborative filtering as well as a content based recommendation system to do item similarity. uh, Although feature based methods are quite popular and they can give us lots of uh, understanding about like our feature dimension of user and item, but they come with lots of challenges. One of the biggest challenges come with feature based system is sparsity and curse of dimensionality. What do we mean by sparsity and curse of dimensionality? So we if we remember, we used to create like a something called interaction matrix, which is a simple matrix that cover both uh, the covers like interaction between user and item. So in the row of this matrix, we used to have like every user, and in the column of this matrix we used to have every item, right? And whenever a user interact with a certain item, we could represent it with like some kind of encoding. So here we have like 0 1 if we are just talking about a simple implicit feedback. Implicit feedback means like if you watched something or you clicked on something without explicitly asking user, we can create just this binary matrix with 0 1 interaction. Or we can also use like a rating explicit feedback where we have like certain kind of rating towards any item, where we have like this 5-star rating for this item from this user. You can also put that encoding here. Uh, Either kind of encoding, the biggest problem we have here is that, like, as the user and feature size grows, uh, you have like huge interaction metric. The size of interaction metric grows as the user and item grows. And we have also seen like something called Matthews effect or popularity bias, where some of the very small set of content have extremely high engagement, that for those particular items you have like very uh, uh, let's say continuously full metrics, full column, I will say. And for rest of the items we have like a very large zeros, or you can say like null metrics. uh, so this problem of sparsity and curse of dimensionality, as we've seen that the user grows, the size of this matrix grows. And also as this Matthew effect and popularity bias comes into the picture, our metrics get more and more sparse. Now, because of these two problems, we cannot use feature-based method. So what we can do? So uh, what we can do, like obviously we would like to use a lower dimensional embeddings that help us to capture more complex relationship in an efficient and effective way. Why do we say efficient and effective way? So as we can see that we have this n cross m dimensional matrix, right? What we are trying to do in this low rank method, that we are trying to convert them into lower dimension matrix like n cross k or k cross m, where k is much smaller than n and m. Now what we are trying to do, we just try to break this interaction matrix I into two smaller matrix, let's say uh, u, like u and v we already used, right? So let's say p and q, right? So p and q, and this p and q matrix will be a much smaller rank matrix than the original matrix. So the n could be like n cross k, and similarly q could be k cross m. Just trying to make sure that matrix multiplication adhere with uh, the dimension. So why we are doing it, like what we are trying to do, we are trying to squeeze this big matrix into these small matrix with certain rank k, and this rank k can be decided by us. uh, what we can do that, when we do this thing, we have two advantages. First, like we are reducing the dimension, so it's a computationally very efficient. Second thing, we are capturing more complex interaction between like user and item. The third most important thing, like when we squeeze these metrics into these lower rank metrics, what we do, like we create this called information bottleneck. Now, this information bottleneck help us to recreate the original metrics when we multiply these like low rank metrics. And after multiplication of these low rank metrics, what we can do, we can reconstruct the original matrix. But during that reconstruction process, because of this less capacity and degree of freedom we have with these two metrics, we can actually fulfill the missing entries of this matrix. So initially, if we have this u and I, and if we recreate metrics with the multiplication of these low rank metrics, what we can do that, suppose we did not have like item rating for this user 10, right? And while recreating this process, we can actually generate an approximate rating for this user with respect to I, and that's help us to predict a rating for item I from this user 10. And that's way we can either uh, choose to recommend or not choose to recommend this item I to this particular user. This is very important property. We have to remember that because of this information bottleneck, it helps us to extrapolate this idea that we can recreate our original metrics using this metrics completion process. So when we go to these lower rank embeddings, what we call them latent space, right? So these latent space are like the low dimensional dense metrics, what we already talked about, where we use this certain kind of approximation method to generate this original matrix. Now, uh, we have to make sure that we choose this rank properly so we can get like more uh, better solution. What do I mean that like suppose we are using certain method to generate this original matrix. In this particular example, what we have that we have this interaction matrix A, and we are trying to use this singular value decomposition technique where we generate like these three metrics. So basically these three metrics are this U and V are the rotational metrics, and S is the diagonal matrix which consists the eigenvalues. Now if you know like linear algebra, what we are trying to do, we are trying to generate eigenvalues of this matrix. And here we are using singular value decomposition because singular value decomposition can work for any kind of matrix, like whether it's a rectangular or like whether it's square matrix, because if you want to use like proper eigenvalues, you have to have like this square matrix. But in the singular value decomposition, you can generate this singular value using this SVD decomposition. Now, what we are trying to do here, that we are trying to generate the eigenvalues, and once we get these eigenvalues, what we'll do, like we set this last two eigenvalues at 0. What we are trying to do, because these eigenvalues are arranged in a decreasing order of the importance. So if you see that the first eigenvalue is pretty high and the second one is like a little bit low or similar, and then the rest of the two eigenvalues are 0, it will help us to understand that how much information we are getting respect to each eigenvalue with respect to each eigenvectors. Uh, Once we construct this singular value, what we'll do the matrix multiplication of these two metrics. Like actually we are multiplying three metrics, but just assume that S and U and S are like multiplied and they are single metrics, and then we can generate like original B matrix. So this, when we compare this B with the original A, we can see that it has like reconstructed lots of values. So if you can see that the first value has been reconstructed to 1.7, the last value has been reconstructed to 7.2, and then you can see that we have like some other values here. Now you might be questioned that why we did not get the full information of the original matrix. The reason is that we actually deliberately set these two eigenvalues 0. And what we are trying to do here, we are trying to force this matrix to generate original values even though we don't have the original eigenvalues of the original matrix. So we are trying to introduce this informational bottleneck here by deliberately putting this S, like last two eigenvalues 0, so we can reconstruct the original matrix. And that's the entire thing about this low rank metric, that what we are trying to do, we are trying to recreate our original matrix. Now, once we create the original matrix, we can use various distance functions because we are now dealing with an higher dimensional embedding space. And in the higher dimensional embedding space, what we really need is like some kind of similarity matrix where we can measure that whether two items are similar or not. And for that, like we have like various distance metrics. One of the distance metrics we can use is like dot product or cosine distance. Now, dot product is between two vector, can be described as u cross p, where magnitude of u multiplied by magnitude of p cos theta, and this theta is the angle between these two vectors. So when we talk about uh, dot product or cosine similarity, we want to choose that which one we want to choose. In the cosine similarity, we will have like more normalized value because we see that we divide this dot product with the magnitude of the individual vector, but we don't do same thing in the dot product. Uh, it has its own pros and cons. When we have like lots of popular item, it can actually influence our dot product matrix. So as we can see here, that if we want to measure similarity between A and B, so we can see that like A cross B is A is very near to B, so we are getting A cross B. We are getting this theta value, but this cos theta value. But in this particular case, we can see that like this metric, this cos theta, as we have seen in the previous lecture, is varies from -1 to 1, as -1 indicate like completely opposite items. One can be seen as like overlapping item, they are like exactly similar, and so 0 can be seen that like orthogonal, or like no match at all. uh, where in the dot product we can see that the magnitude of C is influencing the uh, dot product between. So as we have already seen that the A cross B, like the angle between these two is like smaller, so B should be more similar to A. But when we see that a dot product, because the magnitude of C is so high, in this case, like the dot product is showing A is more similar to C than A is to B. And we can see that the impact of popularity bias here, that if you have a very popular item that has a very high uh, let's say magnitude in the higher dimensional, it can influence your dot product. So you have to choose very carefully which distance metrics you want to choose for your embedding. Now, we have also seen like something called co-occurrence model. So what is co-occurrence model? In the co-occurrence model, we try to create a matrix where we want to see that like how many times certain items comes together. So suppose take an example of e-commerce, right? So suppose you have like a particular type of, let's say, t-shirt, right? And this t-shirt always like whenever someone buys that t-shirt, they always buy this like these pants or shorts, something with it, right? So they always occur together. So in our interaction metrics, we can see that like these two items have like this is t-shirt T, or like this is P. They always occur together like two times, right? Something like that. Like that this co-occurrence model tells us that like how likely these two things comes together. This is very important when we do like certain kind of natural language processing task, where we try to understand that which words come together. So when there are like certain kind of word, like let's say this current tense setting, right? If they appear a lot in a document, then we'll say that the co-occurrence between current and setting is like 2, because they appears together a lot, rather than current ampere or something like that. So uh, uh, in the previous model, we have seen that we were using PMI for co-occurrence model. The PMI is like this uh, is this matrix which measure the co-occurrence between two items. It can be calculated using this P of dot. This is probability of like x and I, x and xi and xj coming together, divided by the multiplication of this marginal probability of xi and xj. So it can be written down as a co-occurrence matrix I, xi and xj, divided by individual xi and xj. Now, what we are here trying to do, that because these are like distribution, right? And PMI is not a distance metric. So the definition of a distance metric that it has to follow, if you follow like previous lecture, it's explained that like the metric should follow certain kind of axioms, and the triangular inequality it should also find. So if A plus B should always be greater than or equal to C, right? This kind of axiom, like it should follow this triangular inequality, and PMI doesn't follow that. So what we'll do, we'll try to create different distance metrics for our co-occurrence metrics. Now, what we use like instead of that is something called Hellinger distance. So the Hellinger distance help us to calculate the distance between the two co-occurrence density, probability density. So how do we do that? So as I already saw, like this is how you create your uh, co-occurrence matrix. That's the simplest way to create a co-occurrence matrix. You know the how to create your interaction matrix I, right? We already discussed that. Like the I interaction matrix is U and I, where if the item U is interacting with I, we just place 1 here or 0 here. And to create a co-occurrence matrix, we just multiply I with the I transpose. I think it's like I transport multiply by like something like that, right? That's how you create your co-occurrence matrix. You just multiply the interaction matrix with its own transpose. And once you do that, you will have your co-occurrence matrix. So once you have your co-occurrence matrix, what you can do, you can use the Hellinger distance between two items to find out how similar they are. And there are other methods like to because we are talking about like probability distribution, right? There are other methods to measure the distance between two distribution like KL divergence. But the problem with the KL divergence, it is not, it is an asymmetric metric, right? It is not a symmetric metric. So uh, just this is some simple information about co-occurrence model, that whenever you have like some kind of co-occurrence model specifically in the item similarity, you can use like the Hellinger distance. Now, yeah, we talked that we can reduce the rank of metrics to solve recommender problem, but they also have their own problems itself, right? So what are the problems we are having when we use this rank reduction techniques? So one of the biggest problem we have that the metrics we are using for like the techniques earlier we used to break down that matrix is singular value decomposition. And the problem with the SVD, that SVD is pretty good method, but it only works well when you have like dense metrics. It does not work very well if you have like very highly sparse metrics or it has a higher singular value, because its eigenvalues and eigenvectors do not establish a relationship that accurately. And also it's a computationally very expensive technique whenever you create like just eigenvalues or eigenvectors, because of the computational complexity involved to run such technique. So even like as I mentioned here, that suppose you have like this kind of metrics like n cross m, and then you break down into nd and vdm, the overall computational complexity of that calculation will be NMD, right, which is a very high complexity. So what we try to do, that we are trying to exploring other techniques that can overcome this problem with singular value decomposition. So uh, as we have seen that like we want to like factor a matrix which is mostly sparse and non-negative or binary, right? It has like lots of non-zero for each item vector, which is widely varied. This is the Matthew effect, which is also known as like com- uh, uh, popularity bias. And then the factoring is a cubic complexity already discussed. And uh, these methods are also require something called imputation, and which usually not available for SVD or other full rank method. So what we are trying to do, we will use like is something called ALS, which is also known as alternative least square method. So we know that like we have a matrix like D square and n cross m. We try to break down this interaction matrix into two matrix U and V. And what we will do, that we will uh, we will first keep one this parameter constant, and we'll vary the another one, u. So we'll keep the v constant and then optimize u, and then we'll keep like u constant and optimize v. This is the optimization technique we'll use. Now this is an approximate solution. This is not guarantee like global minima, but it's better than like just trying to optimize both of them. And we'll see why this is very difficult, right? So just for now we see that like we are trying to updating u with this stochastic gradient descent method, where we have like this eta learning rate. U is the original matrix, which rate of change of u with respect to the like the varying parameter, and we have like a sum distance function d, which is trying to minimize the distance between like a and u, a and multiplication of u and v. And similarly we do for v. uh, Now both of these metrics will update the gradient with respect to their metrics. And for sake of the explanation for this particular example, we'll use like least square method as a distance matrix. So this is like more general form. Now we have seen that like we can use like least square method, which is a minus, as you already know, minus u cross v, like square, like a square u cross v, and then we'll try to like take a root of it. Okay, so what we'll do that we will try to use I think we don't use like root, like we just have to square this one. So a minus uv square. So uh, now this is the one problem we are trying to solve, but there are some other problem with it. Uh, we already seen there is a sparsity problem and there is a non-uniformity problem. So the sparsity is that lots of values in this A are still like uh, empty, and like it's a very sparse matrix. And also we have non-uniformity because they are not like centered in the one place, like it is for because of the Matthews effect. You can see, if you see the heat map of this matrix, some of the regions will have like extremely high interaction, and most of the region is like just empty. To overcome this problem, because some of the uh, we have seen that some of the elements have popularity bias, so we have to their magnitude can impact our distance function. And to overcome that, we will use something called regularization technique. So the regularization technique help us into two ways. First, like it help us to uh, include some variance in the matrix, so we can remove like this popularity bias, and also we can overcome this Matthew effect which we having right now. So, and to overcome the sparsity, we'll use something called like a, a, a weight decay method. Let me show you like how to do this one. So suppose we want to regularize u and v, right? So first we can the first like we to start this process, what we'll do, like we'll use something called weighted alternating least square method. This is this one. So this WALS help us to implement these two regularization technique. So first, we'll use this L2 regularization technique. What we'll try to do, we are trying to uh, uh, add these two terms, like which are normalized by their like number of incidents. So this is like the weighted one, where we are introducing this like L2 term for both UI and VI. And then we will the elegant way to see it is that what we are trying to do, we are trying to minimize the magnitude of the singular values, right? So this is the one will help us to minimize the magnitude of the singular values what we have seen. And the second, we will use like something called Gramian regularization. This Gramian regularization will help us to downsize individual matrix entities. So this Gramian regularization help us with the size of the matrix, and this L2 regularization helps us with the magnitude of the singular values, right? Uh, we'll use both of these terms. So suppose this in this Gramian method, what we are trying to do, we are trying to incorporate like these two terms, which will help us to reduce the size of the matrix. And once we have this both regularization term, we can add it to the original our function. That this is our optimization function is there. And now as you can see that we are like normalizing it with the magnitude, and we are also adding the weighted uh, alternative least squares method. This is our least square term which we discussed previously. And then we have this uh, weight decay, and the second one is that the Gramian regularization. Now we can choose that what the lambda value we want to keep it here over the iteration. But as you can see, this is the complete equation we want to solve to generate these two latent matrix we have like u and v. Now, how to do that? Because there is no closed form solution exists for this equation. So what we'll do, what we did discuss before, we'll use this alternating least squares method to keep one entity constant and try to update another one. And in the second turn, what we'll do, we'll keep like another entity constant and optimize the second one. Now, this is the rest of the talk. We'll talk about the implementation, how to do all this thing in Python. So the book gave this code, and this is very very long code. So I'll try to cover as much as possible. Let's see how we are doing with the time. Okay, so let's start with this, that how to do it. First, we will set up our initial, so this method we are using JSX um, for the matrix factorization, and the reason we are using JSX obviously because it's a very fast GPU and TPU enabled library, which can help us to parallelize this lots of metric operation, and we can utilize lots of this broadcasting and JIT features to uh, you know expedite our computation. So here what we are doing, we are just importing all the libraries, and then we are setting up our one DBs. Now the author did not share the code, the data set with us. This is mostly a template code. The original code can look like more dense. I tried to ask them to get both of the author this data set. If I get it, then I'll implement it and upload it to GitHub. But from right now, we just see the code and try to understand what they are doing. So they are just like first downloading this rating artifact. Once we get the rating artifact, we can have we can get like information about this column, that it has data, number of rows, number of columns. We can read it into a like pandas data frame, and these are like some of the class we are they are some of the methods we are setting up here, which we'll use in the next one. uh, Now here we have a way to divide the data into test and train, which is classical. We want to introduce some kind of holdout fraction where what amount of code we want to put into testing and training, and then we'll apply these like all the operations to extract both user ID and item ID to change their uh, type of rating. Here we are using like not regular interaction metrics what we have seen. So we have seen the regular interaction metric looks like this, right? Now the problem you have seen this interaction metric, yeah, this is like memory, like for memory, it's very inefficient data structure because we are like storing all of them into giant metrics and most of the information is sparse. So what we'll do, we will use this sparse array technique where we will be using a different data representation of to storing these indices and values, and will preserve the dimension, right? So based on only these three values, because we know that like how they are arranged in this matrix, we can actually recreate the entire initial matrix, and that's why we are using this sparse array where we are only storing indices, values, and user and item dimension. This is the normal random function we are using for initialization. As you can see, because this is a JAX and it uses functional programming, we have to make sure that like we are using this PRNG key to normalize our initialize our randomization every time. We'll use uh, this the least square method loss to the mean square error, to compute the mean square error. Uh, then once we will like send it to JIT to just make it like a faster computation to create this computational graph. Uh, Now we are creating this simple class to represent our collaborative filtering model, where we are just giving it like a matrix as a dictionary, embedding ground truth, embedding parameter, and the PRNG key. I already said like this PRNG key important for initialization. uh, then we set up all this different parameters. We'll set up this property to get like this embeddings and like this uh, getter setter for to set up the embeddings or reset the embedding. Once we have that, this is a copy of the previous one. Uh, we can uh, we can also define a class to reset the embedding. So suppose we have like a certain state in our embedding, we want to clear it. We can clear it, and once we clear it, we can actually initialize it with the random normal. So what we had discussed before. So this is what we call like a prior of the embeddings we have. And it is generally advisable that you can start with zero, but the problem is that it will take long time to convert. Sometime it might not convert, so it's always a good idea to have some kind of prior. And the prior we are taking here is the random normal. So this normal distribution will help us to set up the prior. Now we are doing this model constructor, where we are just again creating this entire model. We are creating our training set, we are creating our test set, we are initializing our UNV metrics, we are setting at the embedding dimensional. These are very important. Like it based on like this embedding dimension, you want to decide how much information you want to preserve from the original metrics. The higher that dimension you'll take, the longer the time it will take to optimize. And this is the trade-off between like the efficiency, like the time and the accuracy, like how much accurate representation you want in your metrics. The higher dimension you will take, the more time it will take, but it will more accurate model. But again, like if you want to do a quick training, quick inference, then you should keep like a lower embedding dimension. Now, once we have all of this information, we can actually return this collaborative filtering model with all these parameters. Now we'll start the training. Now in the training process, what we'll do, like again, they are using this weight and bias uh, service where you can actually track your like model training and like all the parameters and artifact, and you can visualize all the graph there. Uh, so first we are doing resetting our embeddings. We are getting all the our like hyperparameters what we want to set, and then we are tracing our gradient because we are applying a stochastic gradient descent technique. Uh, Once we get like all the values, we use this broadcasting technique to broadcast this embeddings and apply this hyperparameters to all the embeddings. We'll start our training, and these are like different, I think, configuration we have used in the sweep configuration to optimize our parameters. What it does is actually test with various parameters. So as we have seen that this is like hyperparameter optimization technique. What we'll do here, like we'll just set up like some range of param parameters here, and based on this range of parameters, this a sweep function will try to find out the optimal value for every iteration. And once it reaches the optimal value, then it will uh, turn off the training, right? uh, Again, we have a once we do that, we want to apply something called cross validation technique, which is a little bit difficult in matrix factorization. So for that, they actually did some more setting. They have used this they have implemented this two regularization technique which we discussed, like this Gramian regularization and the L2 regularization, and we regularize the OM loss. And once we have that, like you can see the total loss is the loss of the mean square error, L2 regularization and Gramian regularization. And then we'll use like something called uh, learning rate scheduler. We'll use like a learning rate decay method to further find out the optimized parameter. Like it's actually start with the higher learning rate and like gradually slows down the learning rate to whenever it tries to find the optimal value. Uh, Again, these are all the various functions has been returned to training with the regularization loss. So previously we have seen that we are not using any kind of regularization, but here in this particular process we are trying to regularize the all the parameters with here. Not only we are op, we are not only optimizing the hyperparameter of the model, but here also optimizing the hyperparameters of the L2 norms and the Gramian one. And once we do all of this thing, this is just a method to uh, again like do all the sweeping of the parameters with different range of the parameters. And after writing this all code, what we can do, we can also set up a cross validation technique, which is k-fold cross validation. And as I said, like in the matrix factorization, it's very difficult to do k-fold. So there has to be done like some kind of data manipulation technique where you have to change this indices in such a way that, and one of the most important thing you want to take away from this one, that the regularization in the matrix factorization is very different than what we do in machine learning. So one thing you should see that, like when suppose you have like some kind of rating system from your user. So your user have this like a rating time system. Suppose like movie recommendation. Like so this movie come like movie A, which has like 5 time step T1, T2, T3, T4, right? And the rating changes all the time. Like let's say the user was giving rating 3 or 1 or something 4, something like that. So in the key fold parameter, like you in the regularization, you want to make sure that your timestamp should be kept in such a way that like you are using a historical timestamp training to predict the future one, right? You cannot do like this, right? You're taking T2 and T3 and like predicting T1, because this is not like causal, right? In the causality, what we are trying to do, we are trying to take like your historical data and trying to predict the future data. We are trying to predict the future rating, right? So this entire process, what we are trying to make sure that like during our k-fold, we make sure that like we are training our data in a causal way. And yeah, this all step is doing the same thing, that we have to make sure that like we keep the fold of like training and uh, testing in such a way that like our cross validation step should also include this kind of structure that should preserve that structure. And only then we can like properly train our model to predict future rating. Otherwise it will also like take like current rating and try to predict the previous rating. So that is not correct. So this is all it is doing. And once we do that, like I think we are up to time now. But yeah, in the next chapter, we'll see that like how this hyperparameters unfold and how much learning we get from this rating. But if you want to like learn more information, I strongly suggest you to go through this code in the book, because it's a lot, and you have to understand in a step by step to see that how we are making sure that like we are training our model in a such a way that like we are keeping this time step intact during our these different folds. So with that, like I conclude this one and I'll stop the recording.